Hello, and today we are going to look at Chapter 2. This is another chapter where we are building our foundation of knowledge regarding science in general, experimental design. We're going to touch a couple topics that are relevant you have learned about in chemistry, and just go over scientific principles in general. So let's get started. The chapter starts with a core case study, and it focuses on the Hubbard Brook Experimental Forest, which is in New Hampshire. And when you read this case study, I want you guys to be able to do the following. Can you identify the hypothesis being tested? Can you identify the controls, the variables, dependent, independent variables? Can you explain how the experimental forest differed from the control forest, and ultimately can you gather evidence whether the hypothesis that was being tested was supported with data or not? So in this experimental forest, scientists were comparing the loss of water and nutrients from an uncut forest, which was the control site, with one that had been stripped of trees, which was the experimental site. And what they ended up finding was that the strip site had 30 to 40% more runoff. And that in the strip site, they also found more dissolved nutrients and more soil erosion. So this provided evidence that the trees in the ecological community here helped with ecosystem services, including the preservation of nutrients in the soil and also water availability. On the next page, we have a diagram that overviews the scientific process, which you guys are familiar with, the scientific method. Know that this is a continual, dynamic process that evolves and changes over time. And even though we may develop theories or laws, when we encounter additional information, we have the ability in science to revise our thinking and even discard our thinking or previous understandings. So know that scientists make observations, we make measurements, we execute experiments, and ultimately we're collecting all of this data to help develop these theories and models and laws that help us best describe how nature works. On our next page, there is a highlight on Jane Goodall. You guys have heard of her before, and her work in animal behavior. Read a little bit about her and her work and research in animal behavior. And know that she also travels and educates individuals and students on what she's learned in animal behavior, specifically her observations regarding chimps. As we continue in the text, we take a look at the process of science and how scientific knowledge advances through this system. And it includes scientists publishing details of their methods and results, and this peer review component, which is very essential, which is a very essential part of the scientific process. So in this process, scientists publish their work, they publish it out in a way that the community, the scientific community, can review the work, and then it leads to this greater level of collaboration and the ability of scientists to confirm and revise their work. Our Science Focus 2.1 over here is focus on a very popular example that's commonly cited in APES regarding the Easter Island hypothesis. Read about this story. We'll watch a video about Easter Island as well. But this is a prime example of how there was a primary hypothesis, an original hypothesis that believed or proposed that deforestation was the main cause of the collapse of a civilization. And over time, scientists encountered additional pieces of evidence and data that suggested maybe it wasn't just deforestation, which allowed them to revisit, rethink, and ultimately revise the hypothesis to include this additional information. On the next page, know that science can fall into one of these three different categories depending on how trustworthy or reliable it is. So tentative science is science that's very preliminary and the results do not have adequate amounts of testing and peer review for it to be in a different category. Tentative science then can advance to unreliable science when there are additional results presented through testing, but we're still missing this peer review component. So it's only after peer review has had an opportunity to occur that the science can then be categorized as reliable. And this reliable science includes the data, includes hypotheses, models, theories, laws, and are widely accepted by scientific experts in that field. Know that science has its limitations, so we know that we cannot, this is an X, we cannot prove anything in science or disprove anything absolutely. What science attempts to do is it attempts to establish the high chance or probability that is something is likely to occur or be an explanation of a phenomenon. Know that in science we do our best to eliminate our own biases, which peer review helps eliminate any biases that a scientist brings into the conversation. But it's hard to completely eliminate a bias from scientific pieces of work. Also know that these systems are complex. We're studying natural systems, and it's not often that we can really hone in on individual variables and relationships among different variables. We are looking at complex interactions, and we do our best to make scientific experiments where we're honing in on variables, but often it is a very complicated web dynamic network of variables interacting with each other. So mathematical models and statistical tools can help us better understand these complex interactions. But again, we do our best, right? So it's complex and we have limitations on our ability to make accurate measurements. So it depends on the type of tools you're using and the accuracy and precision of not only the user of the tool, but the tool itself. In APES, we're going to need to be familiar with some basic chemistry concepts. So some of these terms might sound familiar from chemistry. We should know what these are, and we should be able to navigate the periodic table as well. We will, in this course, become more familiar with specific elements and compounds that are relevant in environmental science. Okie doke, on this page we will need to be familiar with some chemical ions that are listed in table 2.2 along with the pH scale and the compounds listed in 2.3. So a refresher about the pH scale, know that it's a scale that measures the concentration of hydrogen ions. Remember, hydrogen ions are H+. And it's this concentration that's measured on this scale. Things that have a very high concentration of hydrogen ions are going to be on the lower end of this scale. And then things that have a lower concentration of hydrogen ions, or alternatively a high concentration of these hydroxide ions, the OH-, are going to be on the more basic end of this pH scale. On our next page, this math connection, we're going to be applying a lot of math in this course, and one of the skills you guys need to have very confidently down is your graphing skills. So review these requirements here, very basic stuff. You guys need to identify independent and dependent variables accurately when you're graphing. Include a title, labeled axes, which should be scaled appropriately with units, and the numbers should allow that your data takes up the majority of the graphing space. So make sure you keep scale in mind. It's usual to expect at least one FRQ question on the AP test to be build a graph interpret the data and use that in your response. So make sure that you include all of these requirements regularly in your graphs. So take a look at how this data is transformed into a graph. You can practice it, but another tip is whenever time is used as the independent variable in a graph, you are allowed to create a smooth curve because time is continuous and it's believed that these individual points are rather connected in a smooth curve in a pattern like that. Okay, so review these different terms and know how to include or identify those in graphing problems. On the next page, we get a little bit more chemistry. So these are chemical formulas of some compounds that are important in APES. So know those, know their shapes. In chemistry, you guys might have remembered some of these shapes of molecules that are important and may become relevant in the future for this course. So methane, CH4, know that that's a tetrahedral. Like so. These images are shown nicer than my drawing there. Another thing we should be familiar with is that this concept of organic is this term that we use to refer to compounds that make up living organisms or living matter. So know that organic compounds are these compounds that contain at least 2 carbon atoms and fall into these different categories. Note that we also have the exception of methane. So hydrocarbons are molecules that contain both hydrogen and carbon. That's why we name them hydrocarbons. We also have simple carbohydrates along with all of the macromolecules you guys learned about in biology, which includes those complex carbs like starch, proteins, lipids. So know the building blocks of those molecules. Know that lipids, if you think of the triglyceride, that is a type of lipid that is made up of fatty acids, 3 of them linked to a glycerol molecule. Moving on to cells, so know that cells are the building blocks of life, and according to the cell theory, all living organisms are made of cells. There are some additional parts to the cell theory that include that cells come from pre-existing cells, but what's important for us to know is that all living organisms are made of cells, and in multicellular organisms, those cells work together. We also need to be familiar with the concept of how traits arise in organisms. So know that DNA is the genetic information that's stored in living organisms, and DNA stands for deoxyribonucleic acid. The structure is reviewed on a previous page, so remember that these 2 strands are linked together with hydrogen bonds. These hydrogen bonds can be disrupted so that we end up with a single strand of DNA. And through transcription and translation, we can make a copy of this DNA into RNA. And translation, we can convert this RNA into a functional protein product. And it's with this protein that we see ultimately the trait in the organism. So know that it's a segment of the DNA that is participating in transcription and translation to give rise to that protein, ultimately that trait. Another important law we need to remember is the law of conservation of matter. And this states that matter cannot be created or destroyed, but rather that it only changes form. So we can view and observe matter undergoing physical changes or chemical changes. It's in chemical changes that the chemical composition of the matter changes. So we have chemistry happening where there's reactants and products and bonds being broken and being formed. Here we see additional information that supports this law of conservation of matter. So know that we can't create or destroy matter. We can't create or destroy atoms. We have the atoms that are on our planet, and they just rearrange to form different compounds through chemical changes. In this next section, 2.3, we look at what energy is, and energy is going to be relevant in future units. We need to know energy is the ability to do work. We'll know that there are different types of energy. You guys have heard of kinetic and potential energy. We know that heat is a form of energy. There's more different types of energy, but know that there are several laws that describe how energy operates. So we have the first law of thermodynamics and the second law of thermodynamics, which describes what happens to energy as it undergoes changes. On the next page, we see the electromagnetic spectrum. We know that the energy on this spectrum differs in wavelength. So this symbol means wavelength. And you guys have seen this spectrum before. You know that the visible light is a portion of the spectrum. You can review it on page 48. On the next page, we get some examples of the different types of energy and how they're converted from one form to another. So if we have a ball on top of a hill, we see that it has a lot of potential energy because it has the potential to roll down the hill. But it's not until it is moving that it has a high amount of kinetic energy. Then when it gets to the bottom of the hill, it has a lower potential energy. So review these terms, know how to apply these terms to different concepts. Here we have the first law of thermodynamics, or the conservation of energy. And this law basically states that energy cannot be created or destroyed. So it's consistent with the conservation of mass that we talked about earlier, but energy itself cannot be created or destroyed. The second law also describes energy, and it basically states that we end up with lower quality or less usable energy than what we started with. We measure this as entropy or randomness. So know that it changes form through these different energy conversions into less usable forms. In our previous chapter, we have talked about forms of energy, whether they're renewable or non-renewable. Remember that renewable energy is gained from resources that are replenished by natural processes in a relatively short time, compared to non-renewable sources. These are energy that's gained from resources that can be depleted and are not replenished by natural processes within a human time scale. On this next page, we'll find some more math practice. This type of math might look familiar from chemistry, where you guys are executing dimensional analysis. So the big thing here is that you're going to be given a measurement or some kind of quantity, and you're going to have to use that information to convert it with dimensional analysis into some answer. We do that by using our units and canceling them out as we multiply it by different fractions. So we can convert minutes into hours by saying this 38 minutes is going to be multiplied by, this is a unit conversion factor. So we know that there are 60 minutes in an hour. And so if we multiply these out, our minute units cancel out, which allow us to convert our units to hours. So if we do 38 times 1 divided by 60, we'll get our new measurement in hours. So know that the key to dimensional analysis is to always include your units behind every single number you write down. Heading back to our textbook section, we are taking a look at different feedback loops. There are two different types, positive and negative feedback loops. For our positive feedback loop, this is, when we have a system changes further in the same direction. So think of more. When a woman goes into labor, there is an increase in hormones that help accelerate the process to release more hormones and get the baby delivered safely. So that would be an example of positive feedback. For negative feedback, it's more of a correcting system where it causes the system to change in opposite direction. So it's trying to achieve homeostasis or balance or some type of stability, but it's more of a correcting push in the system. So we have some common examples of feedback loops here. Be able to describe the difference between positive and negative and be able to provide examples of each. In the top figure, we have an example of positive feedback, where if you revisit that case study at the beginning of this chapter, it shows that this is an escalating feedback loop. So we see that with decreased vegetation, we have an increase in nutrient loss and erosion that continues to happen in this ecosystem. On our next figure, we have an example of negative feedback. This is an example of how the thermostat in your home helps to correct changes in temperature to achieve homeostasis or stability in the system. These negative feedback systems are more common in nature because there are a lot of examples of a system trying to achieve homeostasis or stability. So before you guys wrap up your notes, I would encourage you guys to revisit these key ideas. There are some concepts, or rather laws, that we will have to memorize. For example, in a free response question, it might give you a scenario and ask you, how is the first law of thermodynamics relevant in this scenario? So be able to reference these different laws, know what they mean, and how they apply to different scenarios in AP Environmental Science.